Have you ever looked up at the sky and wondered why things fall down instead of up? It's a simple question that has captivated the minds of scientists and philosophers for centuries. What keeps us grounded? Why do objects, when dropped, always seem to be drawn towards the Earth? The answer lies in one of the most fundamental forces governing our universe: gravity. Gravity is not just a force, it's a fundamental aspect of the fabric of our universe. It's what holds the Earth in its orbit around the Sun, keeps our feet planted firmly on the ground, and dictates the motion of stars and galaxies across the cosmos. It's an invisible force, yet its effects are felt everywhere and in everything. Without gravity, our universe would be a vastly different place, devoid of the structures and wonders we observe today. The first person to truly unlock the secrets of gravity was Sir Isaac Newton, a brilliant physicist and mathematician. In his groundbreaking work, Principia Mathematica, published in 1687, Newton proposed his law of universal gravitation. This law states that every object in the universe attracts every other object with a force that is proportional to their masses and inversely proportional to the square of the distance between their centers. In simpler terms, the more massive an object is, the stronger its gravitational pull. Similarly, the closer two objects are, the stronger the gravitational attraction between them. Newton's laws of motion and gravity revolutionized our understanding of the universe. They provided a mathematical framework to describe the motion of objects, from falling apples to orbiting planets. His work laid the foundation for classical physics, and continues to be used today to understand a vast range of phenomena, from the trajectory of baseballs to the design of spacecraft. While Newton's laws accurately described the effects of gravity, he couldn't explain what gravity actually was or how it worked over vast distances. His laws were groundbreaking, but they left many questions unanswered. It was Albert Einstein who revolutionized our understanding of gravity in the early 20th century with his theory of general relativity. Einstein proposed a radical idea: gravity is not a force acting at a distance, but rather a curvature in the fabric of space-time caused by the presence of mass and energy. This was a profound shift in thinking. Imagine a bowling ball placed on a trampoline. The ball creates a dip, a curvature, in the trampoline's surface. Now, if you roll a marble across the trampoline, it will follow a curved path around the bowling ball, drawn by the dip in the fabric. This simple demonstration helps us visualize the complex concept of space-time curvature. This is a simple analogy for how Einstein described gravity. Massive objects like stars and planets warp the fabric of space-time around them, and other objects, including light, are forced to follow these curved paths. This warping effect is what we perceive as gravity. Einstein's theory of general relativity has been confirmed by numerous experiments and observations, from the bending of starlight around the sun during a solar eclipse, to the existence of black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape. These discoveries have deepened our understanding of the universe. The dance of celestial objects, orbits and gravity's influence. One of the most captivating manifestations of gravity is the intricate dance of celestial objects in the vastness of space. Planets orbit stars, moons orbit planets, and stars themselves cluster together in vast galaxies, all held together by the invisible hand of gravity. This force is what keeps the universe in a delicate balance, ensuring that celestial bodies move in predictable paths. An orbit is a delicate balance between the forward motion of an object, called inertia, and the inward pull of gravity from another, more massive object. This interplay creates the beautiful and complex orbits we observe. Imagine throwing a ball horizontally. If there were no gravity, the ball would continue in a straight line forever, never deviating from its path. However, Earth's gravity pulls the ball downward, causing it to follow a curved path. This is the same principle that governs the motion of planets and moons. If you throw the ball with enough speed, the curvature of its path will match the curvature of the Earth, and it will fall around the Earth, essentially going into orbit. This is how artificial satellites are placed into orbit. Of course, there's no air resistance in space to slow the ball down. This lack of resistance allows objects to maintain their speed and trajectory. This is why satellites and the International Space Station can remain in orbit for extended periods, continuously falling around the Earth without ever hitting the ground. They are in a state of free fall, perpetually pulled by Earth's gravity, yet never reaching the surface. Tides. the moon's gravitational pull on Earth's oceans. Gravity's influence is not limited to celestial objects in space. It also has profound effects here on Earth. This invisible force is responsible for many natural phenomena that we observe daily. One of the most visible examples of this is the ebb and flow of tides. These rhythmic movements of the ocean are a direct result of gravitational forces at play. Tides are caused by the gravitational pull of the moon and, to a lesser extent, the sun on Earth's oceans. The interplay between these celestial bodies creates the tidal patterns we see. Because the moon's gravity is stronger on the side of Earth closest to it, it pulls the ocean water slightly towards itself, creating a bulge. This bulge is a direct manifestation of the moon's gravitational influence. A corresponding bulge occurs on the opposite side of the Earth due to inertia. This is because the Earth and its oceans are in constant motion, and the water on the far side is flung outward. These bulges are what we experience as high tides. When the bulge reaches a coastline, the water level rises, creating a high tide. Low tides occur in the areas between the bulges. As the bulges move away from a coastline, the water level drops, resulting in a low tide. As the Earth rotates, different locations on Earth pass through these bulges, resulting in the cyclical pattern of high and low tides we observe. This rotation ensures that most coastal areas experience 2 high tides and 2 low tides each day. The sun's gravity also influences tides, but to a lesser degree than the moon's, because it is much farther away. Despite its distance, the sun's gravitational pull still plays a significant role in the tidal patterns. When the sun, Earth, and moon are aligned, during a new moon or full moon, their gravitational forces combine to create especially high tides called spring tides. These tides are higher than usual due to the combined gravitational pull. When the sun and moon are at right angles to each other, during the first and third quarter moons, their gravitational forces partially cancel each other out, resulting in lower high tides called neap tides. These tides are less extreme, showcasing the delicate balance of gravitational forces. Gravity's impact on our daily lives. While we might not always be consciously aware of it, gravity plays a pivotal role in our daily lives, affecting everything from our ability to walk to the flow of rivers. Gravity keeps our feet planted on the ground, allowing us to walk, run, and jump. It's what causes objects to fall to the ground when we drop them. Gravity also plays a crucial role in shaping our planet's landscapes. It drives the water cycle, causing rain to fall from the sky, rivers to flow downhill, and glaciers to carve out valleys over millennia. Weightlessness, astronauts, and the absence of gravity's pull. One of the most fascinating aspects of space travel is the experience of weightlessness, also known as microgravity. While it may look like astronauts are floating effortlessly in space, they are not actually free from gravity's pull. In fact, they are still very much under the influence of Earth's gravity. However, they are in a constant state of freefall around the Earth, much like the ball we discussed earlier. Because they are constantly falling towards Earth at the same rate as their spacecraft, astronauts experience a sensation of weightlessness. They no longer feel the downward pull of gravity, which is why they can float inside their spacecraft and objects appear to drift effortlessly in midair. A simple experiment. Observing gravity in action. You don't need to be an astronaut to observe the effects of gravity. Here's a simple experiment you can try at home. Gather 2 objects of different masses, such as a book and a feather. Hold the objects at the same height above the ground. Drop both objects simultaneously. You'll notice that, despite their differences in mass, both objects will hit the ground at roughly the same time. This is because the acceleration due to gravity is constant for all objects near the Earth's surface, regardless of their mass. Gravity, shaping our universe from stars to us. Gravity is much more than just a force that makes things fall down. It is a fundamental force of nature that shapes the universe at all scales, from the smallest atoms to the largest galaxy clusters. Gravity is responsible for the formation of stars and planets. Clouds of gas and dust in space collapse under their own gravity, eventually becoming dense and hot enough to ignite nuclear fusion, the process that powers stars. The remaining material around a young star can clump together to form planets, moons, and other celestial objects. The universe awaits, encouraging further exploration. Gravity is a force to be reckoned with, shaping our universe in countless ways. From the orbits of planets to the tides on Earth, its influence is felt everywhere. As we continue to explore the cosmos, we are sure to uncover even more about this fundamental force and its role in the grand tapestry of the universe. So keep looking up at the stars, asking questions, and never stop exploring the wonders of the universe around us. Thanks for watching. Do not forget to subscribe. See you in the next video.